This is the fourth colligative property, and we call it osmotic pressure. And this is shown by the symbol pi. The osmosis is the Greek word, and its meaning is to push. So this is a very simple definition of the osmosis. And the osmosis is the spontaneous flow of the solvent into the solution, or from dilute solution to a concentrated solution through semi-permeable membrane, that means permeable to the solvent. So let's have a detail of this osmosis. So what I have written over here in the definition, I have displayed in the two pictures over here. So osmosis is one of the main important thing. That means the two solution or the solvent and the solution are separated by the semi-permeable membrane. There are the two types of the, or the three types of the membrane. One is the maybe the permeable membrane. Permeable membrane, that means which allow all of the material from the solute to the solvent or solvent to the solute. And semi-permeable mean this is only permeable to one of the component, and particularly here we are discussing the solvent. That means this membrane will only allow to pass the solvent molecules. That's why this is called the semi-permeable membrane. And it may be a non-permeable membrane. That means none of the solute and the solvent can penetrate through the membrane, and that membrane is called the non-permeable membrane. So the first important thing is the semi-permeable membrane, and here we are dealing with the permeable to the solvent. That means this membrane will only allow the solvent molecules to pass through from any of the sides, maybe from solvent molecule from this side to this side, or from this side to this side. Now the second one is, and here I have separated the this solvent with the solution, and the solvent here is, that means it is the pure solvent. And why this is going to happen, and you must remember, this is the simple phenomena. That means if this is a pure solvent and this is the solution, that means these black in colors are the solute molecule, and again these light are the solvent, and the whole we call it the solution. And here there is only the solvent molecules are present. So solvent molecules are also available on the right side, and they are also available on the left side. But what is the difference between these two? There are more number of solvent molecules over here, and there are less number of the solvent molecules over here. And this membrane can only allow the passage of the solvent molecule. So solvent molecules from here can also pass to this side, and the solvent molecules which are present over here in the solution side can also pass towards the right hand side. But which is having more passage of the solvent? And of course, on that side, which is having more number of these solvent molecules, or the more solvent molecules are there, there will be the more movement of the solvent molecules from the other side. So this is happening over here. So this is the pure solvent. Pure solvent is separated by the semi-permeable membrane. That means the concentration of the solvent is more. So this is moving towards the solution side to making it dilute, and that is called the osmosis process. So this is one of the example of the osmosis. That means when you separate a solution with its pure solvent, there is a movement of the solvent molecule through the semi-permeable membrane towards the solution, and that process is called the osmosis. Simple. And there may be another way of the osmosis, and when you separate the two different concentrations, like over here is, there is again I have separated with the semi-permeable membrane, and these are the sugar molecules. Look at this left hand side. There is only, let's suppose, the one molecule is present over here. There are the four molecules on the right hand side. And again, this is the, if you consider as the molar concentration, and this is the moles per liter, that means this is having the number of moles. If they are less, then there will be molarity will be low, or you can say this is the dilute solution as compared to the this side. And there are more number of molecules, no more number of the moles of the sugar molecule, that means more concentrated will be the solution. So what is the difference between the two? As I have explained, this is the concentrated solution and this is the dilute solution. So why I have called it a concentrated, based on the number of the moles of the solute. And you can also explain with the number of the moles of the solvent molecules. If and with this simple relationship, molarity is the moles per liter. If there will be more volume, the molarity will be small, or if it is less volume, that would be more concentrated. And same is over here, because here there are the more number of the solvent molecules. Again, if there are the more number of the solvent molecules, that means the dm cube, or the volume of the solvent per liter of the solution is more, and that means the molarity will be the less. So this is, again, this is the dilute solution. So you may also confirm, or you can also correlate the concentration of the solution with respect to the number of moles of the solute, or this is the number of molecules or number of moles of the solvent molecules. So what is happening over here, as displayed over here, there are more number of the solvent molecules on the left hand side. Why they have the more number of the solvent molecules? Because this is the dilute solution as compared to the right hand side. So there is the movement of the solvent molecules. Again, the solvent molecules may pass from left side to the right side, and maybe also from the right side to the left side, because this is the semi-permeable membrane, and this membrane can only allow to pass the solvent molecule to either side. Solute molecules cannot pass because the pores of the membrane are not sufficient to pass the molecules, or the moles or the molecules of the solute. So what is happening over here, again, as I have explained before, there will be the more passage of the solvent molecule from left side to the right side, or I can explain there will be more passage of the solvent molecule from the dilute solution to the concentrated solution, because in dilute solution there are more number of the solvent molecules as compared to the concentrated solution. So there will be more number of the solvent molecules from the dilute solution towards the concentrated solution, and this is also called the osmosis. And you can see over here, with the passage of time, the solvent molecules from the dilute are moving towards the right side, and the volume is decreased over here, and this volume will increase, and this will continue till the equilibrium is achieved. But here I have just explained the osmosis. So as defined over here, so there are two types of the osmosis. One may be from the pure solvent to the solution, or maybe from solvent from the dilute solution to the concentrated solution. Now look at the what is the further. This is an example of the cucumber on the left hand side. It shrivels into the pickle like this in the right side, when it is immersed in the salt water, because the salt water drives the water molecule from the cucumber cells, and this will shivers to this type. And this maybe you can just practice this one at home to visualize the osmosis process. So this is all about I have explained before, and this is just is written for your own notes. So, but you do not have to be confused with the diffusion process. Again, this is just the difference between what is the diffusion and the osmosis. Diffusion is when these solute molecules move from high concentrated to the low concentration. So let's suppose if this is the number of molecules of the solute, they are highly concentrated, and when they are immersed into the solution, they are diffused, and that we know they are diluted. And the movement of the solute from the high to low concentration, that is process is called the diffusion process. But here, this is the movement of the solvent molecules from the low concentration to the high concentration, as I explained before. And this is also one of the example is given. Again, this is the low concentration. This is the high concentration, the solvent molecules from low concentration to the high concentration. And when the solvent molecules move, the volume is decreased and this volume is increased. And that process is called the osmosis process. So coming to the osmotic pressure, which is the most important in our lecture. So osmotic process, simply definition is osmosis process can be prevented by applying this certain pressure, and that is called the osmotic pressure. So let's have a look actually what is the meaning of this definition. So look at this one picture. Here a solution is separated from the pure solvent. This is actually here is the solution inside the bulb, and this is the solvent molecule. Let's suppose this is the water, and this is separated by the semi-permeable membrane as shown over here. So what would be the net passage of the solvent molecule from the beaker through the semi-permeable membrane? Because here this is the concentrated solution and this is the solvent. Of course, the solvent molecules will penetrate into the solution through the semi-permeable membrane, and this process will continue until the equilibrium is achieved. That means there will be no further passage of the solvent molecule inside the bulb or inside the solution which is present in this bulb. That means at that equilibrium, what is the pressure exerted by the column of the liquid in the tube is sufficient to prevent further net passage of the solvent molecule, and that is called the osmotic pressure. That means what would be the pressure exerted right now after the equilibrium is achieved, that is called the osmotic pressure. And here this is our main concern of what is the osmotic pressure, and this is defined over here. So if you keenly look at this picture, and this is just the magnification of the this one membrane. This is the membrane, and the upper side and lower side, this is the solvent molecules on the solution side here, and have a low concentration and therefore pass through the membrane less frequently. Again, because here the solvent molecules are present inside the bulb, but the passage of the solvent molecule from here towards this solvent, pure solvent, will be less as compared to the solvent moving towards the solution. Like over here, the solvent molecules on the pure solvent side have high concentration, and therefore passage through this membrane will be more frequently. So this is the I have already explained in the previous slide, but here This is just the example to show you what is the osmotic pressure, and this is defined over here. So next, the main purpose of this one, actually why we are studying the osmotic pressure, and under the heading of the colligative properties. And colligative properties are defined before, they are the mass dependent. That means if you change the concentration of the solution, this osmotic pressure definitely will change. So that means their osmotic pressure is dependent on the amount of the solute as well. So that's why this is called the colligative property. And this is the final formula actually we use to calculate the osmotic pressure. And this capital M is the molar concentration, and R is the gas constant, T is the absolute temperature. And in the next slide, I'm going to actually derive this from very simple equation. And after the derivation, that means you can calculate the osmotic pressure by using this formula. And you can also calculate the molarity of the solution by using this formula. And from the molarity, you can calculate the number of moles, and then you can also calculate the rest of the weight of the solute or the solvent, as well as we have discussed in detail in the previous colligative properties. So coming to the derivation of the this simple equation, pi is equal to mRT, I'm using three laws, and you have already learned the Boyle's law and Boyle's law for the ideal gas. Here I'm using the Van 't Hoff Boyle's law of solution. So what is this is similar to the Boyle's law. You know, Boyle's law is pressure and volume are inversely proportional to each other. Here the pressure is the osmotic pressure. So look at what is the definition of this one. So at constant temperature, the osmotic pressure of a dilute solution is directly proportional to its molar concentration or inversely proportional to the volume. So in the simple Boyle's law, the pressure of a gas is inversely proportional to the volume, but here we are talking about the solution, not the gases. So that's why this is the Van 't Hoff Boyle's law of solution. So here the osmotic pressure is inversely proportional to the volume. So I am going to explain how this is possible, why osmotic pressure is directly proportional to the concentration or inversely proportional to the volume. So again, if osmotic pressure is directly proportional to the concentration, that means if the more will be the concentration of the solution, more will be the osmotic pressure. This is the meaning. So how it is possible? Again, you may also consider any one of the example. Let's suppose if this is the more concentrated solution as compared to this one, so there will be more flow of the solvent molecules from dilute solution towards the concentrated solution. So there will be more osmosis, and when there will be the more osmosis, that means there will be more osmotic pressure. So osmotic pressure is directly proportional to the concentration, and when you remove this proportionality sign, there will be constant on the right hand side, and that is called, let's suppose it is any of the constant. I'm not going to give its name because I will not be using that constant in the further discussion. So if you want to get the constant, so C is going to divide by the osmotic pressure. So this would be pi over C equal to the constant. So this is the relationship of the osmotic pressure with the concentrations. Now look at the what would be the relationship between the osmotic pressure and the volume. And you know, concentration is the number of moles per liter of the solution or number of moles per volume. And now you can replace the C with this one over with this. So osmotic pressure is directly proportional to N over V. If number of moles are 1, then osmotic pressure is inversely proportional to the volume. And this is the same if there is the more dilution, then the osmotic pressure will be small. And this is the same explanation you may also consider in one of the examples we have used. Again, if it is the more less concentration, that means this is the dilute solution over there, then there will be less movement of the solvent molecule from this side to this side. So osmotic pressure is inversely proportional to the volume. And again, if you remove this proportionality sign, there will be a constant on the right hand side. Let's suppose this is a constant. And when you get the value of the constant, V is going to be multiplied with the pi, and pi V will be equal to the constant. And here, this is defined as I explained, N over V is the number of moles of the solute dissolved in liter, which is particular with the molarity or the concentration we are defining over here. So this is the Van 't Hoff-Boyle's law, and the meaning of this one is the osmotic pressure is inversely proportional to the volume or directly proportional to the concentration. The second, and you also know that Charles' law, the volume is directly proportional to the temperature, but that is for the gases again. But for the solution, this is the Van 't Hoff-Charles law, and at specific or the constant concentration, osmotic pressure of a dilute solution is directly proportional to the absolute temperature of the solution. That means if you increase the temperature, there will be more osmotic pressure. So this is the common phenomenon. That means if you are going to increase the temperature over here, there will be more movement or the randomness of the solvent molecules. So they are going to move more frequently from this side to this side, or from the solvent side to the solution side. So that means by increasing the temperature, there will be more osmotic pressure. And in a similar way, you can also remove the proportionality sign over here. So the osmotic pressure will be equal to constant, and this is the absolute temperature. And if you want to get the constant will be pi divided by T, and this is given over here. The third one is again, you also know the Avogadro law. The volume is proportional to the number of moles. More will be the number of moles of the gas, more will be the volume. This is the Van 't Hoff-Avogadro law for the solution. So at a given temperature, equal volumes of the solutions having same osmotic pressure contains equal number of the solute particles. That means if the solutions have the same number of the solute particle, that means the same concentration, then the osmotic pressure will also be same. So if you increase the number of moles, then the osmotic pressure will be more. And this is similar to the first one. If you increase the concentration, that means you are increasing the number of moles. And if you are increasing the number of moles, then there will be more flow of the solvent towards the concentrated solution. That means osmotic pressure will be more. Again, if you remove the proportionality sign, there will be the constant on the right hand side. This would be the constant, and that would be the N. And if you want to get the value of the constant, that would be pi over N. Simply, this is going to divide over here. Now, similar to the ideal gas equation, now you can combine all these laws, and there we combine them to get the ideal gas equation. And here we are going to get the equation for the osmotic pressure. So this is according to the Van 't Hoff-Boyle's law, and this relationship according to the Van 't Hoff-Charles law, and this is according to the Van 't Hoff-Avogadro law. So when you combine all these two, that means osmotic pressure is directly inversely proportional to volume, directly proportional to the N and T. And when you remove this proportionality sign, there would be the constant on the right hand side. This is called the R, and this is the gas constant. And with this, you would get the same equation. This is the, if you multiply this one, this will be in a similar equation, that is PV is equal to nRT, similar to the ideal gas equation, but here our pressure is the osmotic pressure. So this is the, now I am just converting to our desired, this N over V, I am just separating this one, N divided by V, and NV is the number of moles per volume, and this is the concentration, and this is actually your final equation. And here C, I am replacing the C with the M because this concentration is the molar concentration, because this is the number of moles per liter of the solution. And you can replace this C with the capital M, and this is your final equation, or just this is the rearrangement, and just keeping M at the first, MRT pi equal to MRT. This was our the target to drive this equation. So at the end, I'm just giving one of the exercise how to calculate the osmotic pressure. Let's suppose this is the 1 molar solution of the glucose in water at 300 Kelvin. And what would be the osmotic pressure? This is the very simple equation you can use. MRT, M is the 1 moles per liter. And you have to put the relevant value of the gas constant. Here it is 0.08206 liter atmosphere per Kelvin per mole into, and this is the absolute temperature, this is the 300 Kelvin. If centigrade is given, you have to convert into the Kelvin. When you solve this one, you would get the value of 24.6. So this you have to use the gas constant value, because you have to cancel out all the unit, and this liter will cancel out with the liter, mole will cancel out with the mole, Kelvin will be cancel out with the Kelvin. What is left? Atmosphere is left, and the pressure is having the unit of the atmosphere. So if you put another value of the K for the R, then your answer would be wrong. That would not be the appropriate to use for this calculation. So this is all about the osmosis and the osmotic pressure.